Let's begin with some questions. What is quality assurance and why is it necessary? To answer those questions, let's use a very simplified example. Let's say that this innocuous little gadget you see here is an essential component of a life support system in one of the aerospace programs. Its technical name is unimportant. Let's call it a widget. We'll pretend that the life of an astronaut depends upon its reliability in service. If you were that astronaut and your life hinged upon the proper functioning of this widget, would you be satisfied to accept it for service under the following conditions? Suppose you were permitted to inspect it for flaws, to measure it, X-ray it, test it with dyes, magnetic fields, and so on. In other words, do a type of final acceptance inspection. Would these tests satisfy you, or would you demand more assurance of reliability? If you did accept the widget solely on the basis of a final inspection, you'd be a real gambler. Remember, inspection can only detect certain variations from the design specification. But how would you know if the widget was designed properly in the first place? How would you know if it was handled and stored properly? Or if the workers who made it were well qualified and followed proper manufacturing procedures and sequences? As you can see, unless you know the whole picture, you would not have positive assurance that you could bet your life on the widget. When we talk about knowing the whole picture, we are talking about quality assurance. QA for short. QA is the whole picture. So, let's look at your widget again and try to trace some of the components which form part of the big picture of QA. First of all, we must be sure of its design. In this case, for use in outer space, it must be capable of fulfilling its specified function in a vacuum or at sea level pressure. It must perform under a wide range of temperatures, from extreme cold to extreme heat. It must be capable of withstanding specified vibration and pulling, squeezing, compressive and bending stresses. It must attach to its component parts firmly, and yet must be capable of replacement. It must not leak or rupture. It must stick together so that no particle of it will come loose in service. It must not cause chemical or electrochemical reaction with other components which it contacts. All of these requirements, and many others, must be included in the original design specification agreed upon with the customer or from his contracted engineer. If they aren't, then the designer may very well omit some vital item, either through ignorance or due to cost considerations. But once the first widget is designed, how are we to be sure that the designer didn't overlook something? That's when formal design review meetings should take place. In attendance should be representatives from design, of course, and marketing, production, purchasing, and quality departments, and possibly a customer representative. They will ensure that the customer's requirements have been fully understood and filled, that production is possible, that materials are available, and that inspection and test needs are formulated. Once the design is approved, prototype widgets will be made and tested under conditions much more severe than they will meet in service. When they pass the tests, then future generations of widgets, provided they're exactly the same as the final prototype, will function properly. We have now passed only the first few components of the big picture, quality assurance. We have assured ourselves that the design is satisfactory. This is called design assurance. But a widget manufacturer would still have the task of ensuring that each and every succeeding widget is manufactured in exactly the same way as the original. So he becomes involved in the following type of sequence. The manufacturer of the widget must know that the metal alloy blank from which the widget was machined was made from exactly the same mix of metals as the original widget, and that the alloy mixture was properly formulated under the same conditions of initial temperature, cooling rate, and controlled atmospheric conditions. This means he must have some means for checking the source of these materials, either by direct inspection, acceptance of the supplier's certification, audits of the supplier's processes and records, or by a combination of these. He must know that the welding rod used to join the two halves of the widget is to the same metallurgical specifications as the original rod used in the prototype and has been stored and used properly and by qualified welders. To do this, he requires certified records of rod quality, storage, and handling, issuing time and temperature, and so on. He must know that the welding itself is free from flaws and the welding process did not distort or overheat the parent metal. He'll need to have proof in the form of radiographic films, bend and tensile test samples and records, ultrasonic or eddy current test records, and so on. He must know that the machining of the widget is to the same tolerances as the prototype. He'll require inspection reports, calibration records, audit records, process controls charts, and so on. He must know that the heat treatment of the finished widget is exactly the same as that afforded the prototype. He will require chemical and metallurgical analysis records, traceability records, mill test reports, and so on, and many, many other pieces of information too numerous to list here. Now, we've been using a lot of technical terms and QA jargon up to now. Don't worry, we'll be getting around to explaining all of these and more as we go through this program. Let's summarize briefly. To be absolutely assured of quality in all areas requires three factors: a control system in the form of a detailed quality plan and an organization to carry it out, proper tests and monitoring, and confirming documentation. When these three principles are supplied to each and every step of the manufacturing of the widget, from its design to its final assembly into the life support system, and when our later field experience with the widget has been fed back into the system to confirm or correct the design predictions, then we have the big picture. We have quality assurance. But first, let's emphasize one thing. The customer is not the only beneficiary from a QA program. The supplier should really be the principal beneficiary from his own QA program. Otherwise, there's something seriously wrong with the program or the way that it's being carried out. A good quality assurance program should not only pay for itself, but should add to the profit-making capability of the supplier, the same as any other activity within the supplier's organization. We'll discuss this in more detail on tape 2 in this series. Before we go any further, let's take a short break while you discuss the information given so far. Please turn off the tape now.